in the laboratory of photonics and quantum measurements. And today I'm going to talk mostly on experimental data collection and data processing for integrated microresonators. And just to double check, at the end there will be some short hands-on session. If you want to do some programming a little bit, maybe you need to make sure that you have MATLAB or Python, or if you don't have any, it's fine. I will show you everything. Let's start. And as I mentioned, we're going to talk about integrated microresonators, and I believe mostly you're familiar with them, and you maybe some of you worked with them or saw these cool pictures. And there are many parameters and properties that describe integrated cavities, and mostly we're interested in transmission spectrum, reflection, free spectral range, and dispersion, losses, and coupling rate. Of course, there are many other parameters, but these are the parameters that I'm mostly interested in. And the questions why and how to measure them. And maybe I will not help you with the question why to measure them. That's something for you to investigate, but I will definitely explain you how to measure them and what tools can be used for that and how to process the data. And the trick is that most of the information about integrated microcavities can be just taken out of the transmission spectrum. So this is the main object that we would like to measure. And this is something that we can measure directly, right? So there are no tools that can allow you to measure dispersion directly, right? But transmission spectrum is something that can be simply measured. And yeah, obviously the transmission spectrum is just a graph showing how the light intensity varies with the wavelength or frequency. And usually on the transmission spectrum, you can see resonances and different other features. And there are different contributing factors, of course. And first is just fiber-to-chip coupling, or maybe like a free space beam-to-chip coupling. It depends on how you measure this. It's a technical question. And there are some kind of other parameters like input power, which affects the thermal properties and the nonlinear properties of the cavity. To really get useful information from the cavity, we basically need to maintain very low power for the measurements to keep these measurements linear. Because if we use very high power, of course, we trigger nonlinearities, we trigger thermal response of the cavity, and our measurements, in this case, not going to be very representative. And here you can see like half-processed example of the data trace. And like these sinusoidal oscillations, for example, they just come from the reflections between chip faces. So it's just input and output faces. They have some reflections, they create some kind of Fabry-Perot cavity. And this is something that basically can be, I mean, we can deal with it like in the experiment. We can use some tools to fight this, or we can just use some data processing to get rid of this. And it's quite important sometimes to know what we can do experimentally to improve the data and what we actually can ignore a little bit and then just process this at the end. And as I mentioned, all the important parameters like FSR of the cavity and dispersion, loss rate, and the coupling rate, all of them can be obtained just from a transmission trace. But this transmission trace should be properly measured. And I mean, obviously, how you can measure this, you can just take the chip, take this microcavity, take a laser, sweep the wavelengths, and measure this. And this measurement is going to be very bad. Unless we have like a ultimately good laser, but they do not exist. So first of all, we're interested in making really broadband measurements, because if you measure just a few points, like 100 points, 100 points, that doesn't really help, because mostly, as you might be familiar with this topic, for example, for the soliton generation, we need anomalous dispersion. But for really broadband frequency comps, we need slightly anomalous dispersion, so it's very close to zero dispersion, which means it's very flat. And when something is very small, very flat, it's a little bit hard to measure. So broadband measurements really help here. That's why, for example, we can use how we do this in our lab. We can use a few lasers connected to some MEM switch, and then we sweep one laser, then sweep second laser. And in this case, we can collect really a lot of data over the large frequency span. Then the main measurement part, this is just example of the system. Oh, sorry. Yeah, so this is just an example of the system, how it works in our lab, but it's pretty much the same in other labs. So As you can see, just for the single chip, we have a different measurement optical paths. So in a single run, we can measure like simultaneously transmission spectrum, reflection spectrum, so-called input spectrum, which is just required for calibration. Yeah, as you can see, it's just directly from the laser to the input. And then we have some phase measurements and OFDR that I will explain a bit later. And it's already good, but it's still not enough because, as I mentioned before, besides the measurement, we need calibration. Yeah, so it's just a picture how it works. And the calibration part. This is very important because when we use the laser usually shows the wavelengths. But if you tune it a little bit more, a little bit less, it's not really reproducible, and you don't really know what is the absolute wavelengths because essentially you just change the current. You cannot change the wavelengths of the laser directly. And we need some tools to really calibrate the wavelengths, the frequency of the laser, to really know what we measure. And here there are a few tools that I use for that. So first one is just the gas cell, and by observing the transmission spectrum of the gas cell during the laser scan, we can calibrate the absolute frequency shift. And what is more important, there is a frequency comb installed here. Yeah, so we use frequency comb to measure frequency comb. This frequency comb is required for the absolute frequency axis calibration. More information about this you can find in this article. Basically, the idea here is that frequency comb, as you may know, it's a set of laser lines, but they're all spaced equidistantly, which means that if we can somehow map these lines to the frequencies of our lasers, we can somehow calibrate this. And basically, this is how it works. So it's described in this paper. It's actually a very simple idea, but at the same time, I think it's really cool. So when we see our laser, we can beat our laser with frequency comb, and this will create just a bunch of different other bit nodes. And it's not really helpful until we filter them out. So if we can filter out bit nodes with a very narrow bandpass filters located at some specific frequencies, in this case, the bit node will go to the detector only where it goes through the bandpass filter, obviously. And in this case, we can create a set of markers. So we just call them comb markers. And then we can use them to locally rescale the frequency axis to like stretch it a little bit or squeeze it a little bit. And this gives a really, really precise calibration of the frequency axis. And that helps a lot to improve the measurements. So this is just an example. As you can see with the green line, it's a normalized transmission trace of some sample of some cavity. And basically this blue and the red lines are just different comb markers that are used for calibration. And obviously for the absolute transmission calibration, we need some ideal reference, because every time we measure something on the chip, we need to compare this to something. And just the easiest way to think is that just a piece of optical fiber can be just a sample that has absolutely nice transmission. So we can calibrate. And yeah, as I mentioned, we need to keep low power. So that's very simple. We just put attenuator here, and we control the power to maintain a good signal to noise ratio and the power. And it's just example of some data traces, how it can look like. And as you can see here, so we have some transmission trace. And as you can see, the shape of it is defined not by the cavity, not by the sample, but it's actually defined by the laser function. Because laser cannot produce the same output power at different wavelengths. It's a complex system, and it has some fluctuations, some variations. So we should take them into account. Here we come to the dispersion measurements. So I believe you are familiar with the concept of dispersion, and you know why we should measure this and how important it is to design the cavities that can actually produce solitons or frequency combs. Because if you just put some parameters for the fabrication and they're not really good, it's really hard to get something experimentally. But on the other hand, sometimes you can prepare a really good design, you can do like really good simulations, but at the end you still need to work like with a real device, and you need to measure and process like the real device, not the model. And as it's well known, the dispersion can be represented in this way. So basically, for each mode of the cavity, there is like a central node that you're gonna pump, and then just a set of lines separated by free spectral range, and then some dispersion coefficients that basically show you how the lines get some frequency shifts. Yeah, it's just an example of the transmission spectrum. And basically here are the resonance marked, basically that we need them for the data processing. Here is the trick. Not all of the resonances basically contribute to the dispersion. And from here, it starts to be a little bit tricky, and data processing should be very careful. And sometimes it's really hard to make it like automatized, so you really need to pay attention to this. For example, here you can see some small resonances, but those are probably some resonances of a different mode that you don't need to take into account. On the same time, some resonances might be not really found in your data processing. For example, as you can see here, this resonance was skipped. Yeah, that's why sometimes data processing really takes quite a lot of time, and you need to put a lot of efforts. And just as a side note, is anybody familiar with optical frequency domain reflectometry? Not really. Okay. So the trick is that if you have a cavity, if you have a resonator, which has resonances, obviously, it's quite simple conceptually how to measure the dispersion. But if you have like a long structure, we need to use a bit different technique, which is called OFDR. So this is just a side note. I'm not going to talk much about this, but just for you to know. So the OFDR measurements are called, like, as I said, optical frequency domain reflectometry. So that means that when we have the laser and we sweep the wavelength of this laser, we can compare the reflection from the sample with some kind of ideal reflection. And then by processing the data, we can basically see the reflection slope along the sample. So for example, this like 2 meter long spirals, we can see how the reflection slowly decreases. So this is how we can analyze losses, but at the same time, due to the dispersion, the reflections from chip facets, they will move a little bit, changing the distance. So that's how we can analyze losses and dispersion in long structures like spiral waveguides, but not the cavities. And yeah, just an example of how the data can look like, but that's just a side note for you to know. And going back to cavities. So as I said, to basically measure the dispersion, we should find the resonances, we should identify those peaks, and basically it looks simple because we just need to do some kind of fitting of this dispersion, and then we are happy. But the problem is that there are really a lot of technical details. So for example, if one of our resonances looks like this, it's going to be fine. When we find the peak, it's just right here. It's not going to affect any of our data processing. But for example, in this case, this resonance looks a little bit noisy, and okay, just a simple script finds that the peak of this resonance is here, which means that if you're going to process this data further, it's not going to be really correct. And mostly all the data is noisy, so it happens like every time. And to make it like really properly, we need to fit every resonance. That's why we need some kind of theoretical models to do that. And basically, this is just the simplest model. It's just a Lorentzian peak. And as you can see here, it includes basically kappa naught and the kappa x, which is respectively just cavity losses and the coupling rate. And there is a small trick. As you can see in this equation, kappa naught and kappa x, they kind of can be changed, and the equation doesn't change. So are you familiar with like undercoupled resonances or overcoupled, right? Yeah. So do you know how to distinguish if this resonance is overcoupled or undercoupled?
And if it drops to zero, it's critically coupled.
Yeah, it drops to zero if it's critically coupled. But if it's undercoupled or if it's overcoupled, it can look the same. It's just a little bit above zero. But how to distinguish overcoupled and undercoupled? I mean, in theory, it's very simple because in theory, you have like this number, and this number tells you what it is. But in reality, you have this resonance, and you don't know if it's undercoupled or if it's overcoupled. Yeah?
We got kappa 0, kappa x over
the delta, and then you have the curve which drops to here and then bounces back again.
Yeah, I mean, you can plot, but how to extract this data from here? I mean, we have just a resonance. You don't know if it's overcoupled or undercoupled.
Can we use something like this cavity return method so that we set the
We can, but that's a bit too complicated. It's overkill. I mean, you can, of course, yeah, I mean, but imagine you have a cavity with like thousands of resonances. You're gonna do this ring down measurements for each cavity? That's not gonna work. As you can see here, if I just process all my resonances and I fit each resonance with Laurentian peak, my all kappa naught and kappa x, they're all swapped. And you really don't know what is happening here. And the trick is that to process this data, we need to take a look at the phase. We need to take a look at the phase of the resonance. Because for different resonances, the phase changes differently, as you can see here, with respect to the tuning. Not only the transmission, but the phase as well. And by analyzing the phase, I mean, this is how one can check if the cavity is if the resonance is overcoupled or undercoupled. And in this paper, it's a really good example of how it works. So here you can see a sample with like a bunch of different resonances. And for different resonances, it shows how basically the phase behaves with respect to the tuning. Yeah. So this is kind of the tool. But actually, for many samples, there is a little bit, I mean, there is one small trick. If I just go back to the transmission trace, just a few slides back. There is one simple trick how we can analyze like if mostly resonances are like undercoupled or overcoupled. If you can see here, they have some kind of trend. They go up like this, which means that mostly they are undercoupled. Yeah, so if resonances are coupled, yeah, so it's like transmission trace. Yeah, and one resonance go like this, second like this. So this is like critically coupled. And when they go undercoupled, the overall trend will be like this, because when we increase the wavelengths, when we increase the frequency, we decrease the wavelengths. And when we have like this cavity waveguide and the bus waveguide, of course, with smaller wavelengths, coupling drops, and that means it's getting undercoupled. Yeah, so usually when we increase the frequency, we get undercoupled. And here is exactly what you can see. By this trend, you can see that it's undercoupled. And if this trend was like a vice versa, like this, then you can immediately say that mostly all the resonances are like overcoupled. But still, sometimes you need to process like each resonance separately to see how it works.
Sure. So how would you measure
Good question. Let me go back a little bit. Yeah, so here in this experimental setup, you can see this photo receiver for the phase. Basically, obviously, you cannot measure the absolute phase. The absolute phase doesn't exist. If one would ever measure the absolute phase, it's like 10 Nobel Prize per year, I mean, for this. But you can always measure the relative phase. And this is very simple. You just measure the bit node that goes through your sample with some light that goes directly from the laser. And then by the interference, by analyzing the interference, you can basically extract the phase data. I actually think I added this article to the literature folder that basically shows how using the Mach standard interferometer with the swept laser measurements and then a Hilbert transform, how we can use this to basically extract this phase data. And it's detuning. It's just detuning. Yeah. Yeah, and as shown on this picture, basically here is the phase data. So like this is how the phase changes like over the whole transmission spectrum. And of course, phase cannot be less than 0 and more than 2 pi. That's why kind of every 2 pi it kind of drops back. Yeah, and it just goes down a little bit because there are many resonances. and all this resonance like overcoupled here, which means the phase flips like this. That's why this trend goes a little bit down. But here it's vice versa. This cavity like looks a bit different. That's why it like slightly goes up. So this is kind of how it works in the real experiment. And obviously we are interested quite often not in a single resonance, because this is how some people can manipulate the data. You just measure thousands of resonances, find the best one, put that like your kappa node is like 1 megahertz, and then you say like, oh, it's the best resonance ever, the best resonator ever. But that's not how it works, because for some specific frequencies, okay, it might be that there are not so many defects in the chip that affect this particular frequency. And what we're interested in statistics. And if one was to just to plot the statistics, this is how we can see that basically in average our losses are like of this level. And yeah, it's one of the most important things to do is always remember about 2 pi coefficient. So I already was saying to my colleagues that when I was preparing the slides, I put the slides like, guys, remember about 2 pi. And then I double checked my script and I realized that I missed 2 pi. So that happens. And it just happens because a lot of theory is just developed for this like omega frequencies, but naturally in the real world we work with just frequencies in terahertz, which are like 2 pi different from omega. And that's why we need to basically sometimes correct the values that we calculate or we fit in the measurements to make sure that we represent the real values. Because if we show somebody like, okay, kappa node, like average kappa node for the resonator is like 10 megahertz. That sounds really great until we multiply this by 2 pi. Then it's going to be almost 60, a bit more. And that doesn't sound really great anymore. So going back to the dispersion fitting. As I already mentioned, it's not like you find the resonances and then you just fit all of them and it's going to work smoothly. That's not the case. You really need to struggle a little bit with scripting, with programming this. And sometimes it's like manual selection of different resonances, because once you find the resonance, like can create a data set of this, like create an array, and then you have like first resonance, second, third, fourth, fifth, sixth, seventh, but they do not correspond to the cavity modes, because obviously there is a cavity mode here, there is a cavity mode here, they will just not found in the script. That's why you should be really careful with data processing here. And yeah. Okay, that's what I said. So basically, one approach is just really manually select every resonance and process it, or better solution, because first, kind of when we do the fitting, we select the pumping frequency. So usually it's like corresponds to 1550 nanometer wavelengths. Then we need to determine the FSR of the cavity, which is this D1 parameter over 2 pi, obviously. And basically, if we just do a linear fit of our data, that's going to give us only the approximate FSR, because some resonances are missing in this data. And when you do everything properly, when you like try to iterate a few times your routines, then at some point you're going to end up with something like this. And this is a typical plot that shows how the integrated distortion looks like. And actually, this data can tell you a lot. So first of all, from this data, you can identify what is the D2 coefficient, which is probably one of the most important parameters of any integrated cavity. And just generally by observing different trends and like local features, you can see and you can say whether there are some mode crossings or which is which resonance is better to pump. For example, if I need to make some soliton pumping experiments with this cavity, I would not put my pump somewhere here because there are mode crossings. It's going to affect it a lot. So for example, here I would shift, I don't know, like somewhere here, it looks a bit more flat or more smooth. And obviously, it's not always that your like real device parameters correspond to your simulations and your design parameters. So sometimes you might need to shift a little bit your pumping frequency just to adjust the dispersion and see how it works. Yeah, and usually it doesn't happen then during a PhD. You just measure one cavity, you process one resonance, and it's fine. You never do it again. Usually you need to process a lot of samples. Mostly they don't work. They're really bad. Then you do it again and again. And a very convenient way is kind of invest some time into setting up some scripts, some programming routines that you can use later already for free and iterate it many times. So how we do that in our lab, we have some we have a bunch of different MATLAB scripts that are united like in a single program. And as you can see in this program, we can really analyze different types of data and of cavities. So basically, it's just an example of how it looks like. We can just upload here all the calibration data, all the feed all the resonances, normalize it, and plot all the histograms. And maybe at some point I need to fix this typo because it's not terahertz, obviously, but yeah. This would be very bad if it's still at terahertz. But maybe at some point I will fix this typo in the script. Yeah, so basically that's it about the theory. So either we can do like a short break, or if you have like any questions, and then we can go to the exercise session. Okay?
No break.
No break. Okay, no break. Okay. Breaks are forbidden. Okay. Okay. Any questions? Sure. Yeah, sure. So basically, let me go back a little bit. Yeah, so this is basically just an example of these arbitrary oscillations. They usually look kind of sinusoidal or sinusoidal squared. And first, it's important to kind of normalize data to 1, which I didn't do that, just to speed up a little bit. But yeah, sometimes it's quite important to normalize data to 1. So you have like really normalized transmission. And to get rid of these sinusoidal variations, it's just kind of a moving sinusoidal filter. Yeah, you can just check. It's quite many of these moving filters in some MATLAB toolboxes, and it's a lot of theory. So basically, just select some small window, you fit it with just sinusoidal function, or better sinusoidal squared. Then you move it like a little bit further. You fit it again. Then you move it a little bit further. Fit it again. Then you kind of check like what are the common parameters of the data you fit it, and something like this. And in the experiment, what you can do, you can apply some so-called index matching gel to basically reduce the difference between refractive indexes of your chip and the fiber and the air. And yeah, this is how you can reduce these reflections, but that's a dirty way of doing this, I would say.
Index matching gel?
Yeah. Yeah, I mean, because refractive index of the glass is like 1.4 and the air is just 1. But when you put this index matching gel, then between your fiber and between the chip, it's really less reflective. I mean, you probably will still observe some tiny variations, but it's not going to be that bad. Yeah, so usually it's just a moving sinusoidal filter. Okay, sure.
I have a question about the split resonances.
Mm-hmm.
So is it enough to just split through the resonance?
Yeah, for that you need to really like check the theory kind of, because it can depend on your kind of model and on your purpose. For some applications, it might be just enough to use like 2 Lorentzians, but to be honest, there is just a bit more advanced theory that shows you the splitting. Yeah, you can consider like the forward propagating mode, like the back propagating mode, and then there are equations that basically show you how the transmission spectra should look like in this case. Yeah, so it's gonna include kappa naught, kappa x, and maybe some gamma parameter describing the splitting. Yeah, and yeah, if you need something like really more advanced, if you measure like some, I don't know, some novel tricky cavity with some new physics, maybe you can come up with some like more advanced model, maybe that can include, I don't know, like some thermal response or nonlinear absorption, like whatever. It depends. But yeah.
When you do your picking on the resonances, actually it's between 0 and 1 with which value did you normalize? How this transmission works?
You mean Where? Here?
Yeah.
No, here it's not normalized.
No, but in the fitting, on the Zoom resonator.
Okay, let me go a little bit back.
Okay, so
Here? Yeah. So here, the trick is that for the fitting, I just added some coefficient here. I just put this into the brackets and added some coefficient to change it a little bit.
sorry, I didn't understand. You don't need to normalize the resonance?
It depends. It depends. So usually, if you normalize the whole transmission trace, right? But in this case, the transmission trace looks more or less flat. It looks more or less good. So I just decided to skip the step just to simplify the routines a little bit.
Okay.
So in principle, yeah. And in practice, you see in this equation, it kind of never goes below like 1, if you look far away from the resonance. But what I did, I just put the brackets here, added like one coefficient, and I just normalize like to this coefficient.
Okay, so you don't really normalize when the transmission trace is
Yeah. If it's more or less flat and good, it's not required. And I mean, it really depends on your purpose. So for me, it was just a teaching purpose, so I skipped it a little bit. But if you really need to investigate like in depth the behavior of your cavity, you should be a bit more careful about data processing, and it's better to normalize. And again, it's better to normalize like not the whole transmission trace, but with some moving filters.
yeah. Then with which function you normalize?
Yeah, I mean, what you can do, if you can just like find the baseline, yeah, and usually how we do it is just some splines with like a 10 gigahertz window, for example. Yeah, just cubic splines. Just cubic splines. You take like a 10 gigahertz window. Yeah. So for example, here you take like this window like of 10 gigahertz, and you just use some kind of move-mean averaging to make the curve like a bit more smooth. And then you just fit it with some spline, just a cubic spline, just cubic function, and yeah, you just normalize it to this. Because what you need to normalize actually is just really like large scale variations. You cannot normalize noise, obviously. Yeah, that's why kind of you need to get rid of noise by smoothing the function, and then you can fit it with a cubic function just to really take into account like large scale variations. For example, over like 10 gigahertz, because you don't want to normalize features that are like 5 megahertz, right? Because 5 megahertz is basically probably just a noise. Yeah. Okay, sure.
Can you please go to the next slide? Sorry, it's 31. Slide number 31.
31.
31, yeah.
Okay.
So how do you arrive at, how do you get this float, like amplitude versus the length using OFDR? Can you please explain how you did it?
Yeah, sure. So how the OFDR techniques works? Let me go back to the setup. Yeah, here we go. So first of all, if you like really need to know OFDR in depth, you're going to probably check this article. And the trick is that we have, so first we're setting the lasers, right? We're setting the lasers. And then one photodiode measures what goes through the sample and basically what is reflected in the sample. Because in the sample, we have some reflections, we have some scattering, and the light just going to be reflected backwards. And then we can measure the bit nodes of this reflected light with the direct input from the laser. And then we're going to get some bit nodes, and then we just do Fourier transform. And since we have these bit nodes in time domain, we do Fourier transform. We get them in the frequency domain. So we can, and then we can get the trace that shows you the amplitude of reflection with respect to the time, basically. But okay, time you multiply by the group index, you're going to get the distance. Yeah. And okay, here it works a little bit differently because here it's like not really OFDR because there is no like sample reflection. Usually people use some like a super reflective mirror, like a reference. But here we use just direct input from the laser, which is fine. Yeah, so this is kind of how it works. And then first of all, you can extract losses from this data by observing the slope because further you go into waveguide or into fiber, the amplitude decreases and the reflection gets like really low. Yeah. And second, you can measure the dispersion, because if you have like this waveguide trace, like this is amplitude, and this is length. So you have some noise here. Then you have strong reflection from the input facet, from the chip. Then you have like this decreasing reflection because of losses. And then you have a second peak as a reflection from the output facet. But the trick is that as light of different frequencies accumulates some phase difference within the waveguide, which means that it's different optical lengths for the different frequencies. Which means that in the optical distance, for different frequencies, this peak will be displaced a little bit. And by analyzing how this peak is displaced for different frequencies, you can get the dispersion. Sure.
And without here, how do you estimate the phase that you have two lasers meeting? Like, what is the two lasers doing the 90 times per year?
Yeah, so basically, you have just a laser input like directly from the laser,
Yeah.
and then you know the like let's say what can be like considered let's say the absolute phase of this laser, kind of, because it just changes it changes in a time kind of and you know how it changes this time because it's just sweeping the frequency, so you know how the phase changes, and then you have your cavity, and you don't really know how the phase changes in the cavity, but obviously it changes somehow. And then you can just measure the bit nodes, and by analyzing the behavior of bit nodes, basically again it's just doing the Hilbert transform. You can see whether the phase in the cavity is accumulated like more or less compared to the original phase of the original laser. Because if you beat like two identical lasers, then your phase curve will be just you go like this. Yeah, you just straight. Yeah. But here you have some changes, so obviously you can track these variations.
Yeah. So use both the lasers for the bit node.
No. I mean, for the bit node measurements, you just measure like the direct input from the laser, and then the input from your sample, and you beat this. So kind of to simplify the scheme a little bit, it's like you have the laser here, right? Then you like go to the photodiode, and then you split it here. Here you measure your chip with the cavity, and you beat it. Yeah. And just to simplify the scheme. Yeah. And then you sweep your wavelengths, and by analyzing the bit node trace, you can extract the phase data. If you're more interested, just drop me a message. I can share the article that basically describes all the routines, how you need to work with Hilbert transform to do this. Okay, more questions? Or we go to the exercise session? Okay, let's go to the exercise session. It's going to be very simple because you don't need to do anything. You just need to run the script and that's it. Yeah, basically, I'm going to do the same. So in the folder with materials for the course, there are different scripts, one for MATLAB, one for Python. They are more or less identical. So for those who don't have MATLAB, you can just use a Python script. It also works just by clicking on the run button once, and that's it. But we can just quickly go through different steps in the scripts to see how it actually works. And yeah, so I can give you some time to open MATLAB or Python or upload the scripts. Just let me know when you're ready.
Also, maybe point out that they need to change the path.
Yeah. So yeah, that's a good point. Yeah, to basically upload the data, you need to change the path to the data sets. Yeah. So
Just there, everything else just works.
yes. Everything else works. Yeah. Thanks for nothing. Yeah, so let me know when you're done changing the path and when you can run the first cell. Okay, it's very simple. And when you can run the second cell, if you don't get any errors, when you can really upload the data to your workspace, then just let me know and I will continue. All good? Or any issues? So did it work for you guys? Okay, okay, all good. Okay. Need some help? You mean it worked or you need help? Okay. Are you sure you uploaded the current? I think it's pretty straightforward, but if you need help, there's 3 bar bars. You run just simple script. Yes.